Hello everyone, welcome back to Analog Snippets. In this video, we will continue our discussion of efficiency and losses in inductive switching converters. There are several kinds of losses in inductive switching converters. In the previous video, we went through the first three of these losses. And we said that these three losses can be simulated very accurately in the simulation tools. In this video, we will consider magnetic losses in the inductor. Diode and BJT losses need to wait for another video. In switching converters, inductor is source of several kind of losses. We already looked at the ohmic losses in the last video, which is associated with the DC resistance of the inductor coil. But there are several other sources of losses which are related to the magnetic property of the inductor. Top two of these losses are associated with the inductor core, and hence these losses are also known as core losses. The bottom two losses are related to the increased resistance at the high frequency, and these are usually modeled by AC resistance. Here I should remind that inductor current can be decomposed into two components. For example, this inductor current waveform can be thought of as an AC triangular wave riding on a DC current. The ohmic loss or conduction loss, which is also known as copper loss, is associated with the DC component of this current, while these losses mentioned here are associated with the AC component of this inductor current. At high load current, contribution due to the AC losses can be very small, but AC losses can be major contributor at low or no load conditions. Okay, now let's look at these losses in some more details. Hysteresis losses are associated with the magnetic domains in the core material. Core material is built up with the tiny grains of the magnetic domains. Volume of these domains is roughly 10 to power minus 10 cubic meter, which is slightly smaller than 1 millimeter a side, and it contains roughly 10 to power 19 atoms. All these domains can be considered as tiny magnets. In an unmagnetized core, all these domains point in random directions, so there is no net magnetic field. But under the influence of an external magnetic field, all these domains tend to align to that magnetic field. At sufficiently large magnetic field, all these domains are aligned and core tends to saturate. This behavior can be plotted on a BH curve. Here, external magnetic field is on the x-axis and the magnetic flux is on the y-axis. Let's start with an unmagnetized core where both H and B are 0. Then we apply an external magnetic field which generates magnetic flux in the core material. And at sufficiently high fields, the magnetic flux saturates. When we reduce the H back to 0, the curve doesn't trace the same path. When H reduces back to 0, there is still some leftover magnetic flux in the material. And this happens because not all domains return to the original random direction. To completely demagnetize the core, in fact, we need to apply some negative field now. And if we keep increasing the field in the negative direction, the flux again saturates. Something similar happens if we again reverse the direction of the field. And we can see here there is an hysteresis associated with this curve. And this hysteresis is associated with the loss. The intuitive explanation of this loss is that the back and forth of these magnetic domains requires some work. The number of times you repeat this process, higher will be the loss. So to the first order, the hysteresis losses are proportional to the frequency. Losses are also proportional to the area under this BH hysteresis curve. So to the first order, it is proportional to the square of change in magnetic flux density. Also, bigger the volume of the core, bigger is this loss. Here A represents the area of the core and L is the length. So A cross L is the volume of the core. In reality, this equation is more complicated than that and also varies from core to core. Empirically, this loss is given by Steinmetz equation. Here, Pc is the total core loss, K, alpha and beta are the Steinmetz constants, F is the frequency of operation and delta B is the change in magnetic flux. Alpha is usually between 1 to 2 and beta is between 2 to 3. One point to note is that in a typical switching converter operation, B may not reverse the direction in each cycle. It may very well remain positive or negative all the time. But the core losses still happen because this equation contains delta B. So BH curve in a typical application may look something like these small BH curves. Okay, all this is well and good. But how do you incorporate these core losses in your efficiency calculations? After all, magnetic flux is not something that a typical SPICE simulator simulates. So you can use three approaches to incorporate core losses. First way, you can do hand calculations. Many vendors provide elaborated plots for the core losses. For example, here core losses are plotted for several frequencies. Now, I agree that there is certain charm to do hand calculations using these plots, but it's not very practical or convenient if you have several conditions to cover. So you can do the next best thing an engineer can do. Write a script. Although this Steinmetz equation contains delta B here, but you can modify the equation to contain delta I rather than delta B. Recall that total magnetic flux is related to current and magnetic flux density by simple relations. So it is possible to derive an equation between magnetic flux density and current for a given inductor. Then you can feed delta I to this equation using your simulations and get your core loss. Now these equations written here are just for illustration purpose, and to make the point that it is possible to replace delta B by delta I. Now the third way is even more simple. Just simulate it. Some vendors provide inductor models that can mimic core losses. For example, consider this model. In DC conditions, current only flows through the inductor because this capacitor is open and blocks the current path. But the AC current flows through this path as well. And since there is a resistance in this path, it's a lossy path. The actual models are much more complicated, but this explains the concept. Whichever way you use to calculate the core losses, just keep in mind that it will not be super accurate. So add some guard banding in your calculations. I will not discuss eddy current losses in this video because, truth be told, I have never worked with it. I tried searching several books and online articles but could not find a good reference. Eddy current losses is a well-known phenomena, but I could not find any reference which accounts for eddy current losses in conventional switching converters. So if you are aware of any resources, please point it to me in the comments. I will briefly touch upon the skin effect. Let's say we have a wire with certain thickness. A DC current flows through the entire cross section of this wire. But as the frequency increases, current tends to crowd at the outer layer. That means at the higher frequency, current does not utilize the entire real estate available to it. As a result, resistance increases at the higher frequency. Skin effect is characterized by skin depth, which indicates the thickness of the material where the current flows at a given frequency. A typical skin depth plot looks like this. So skin depth reduces as frequency increases. Skin depth of copper at 1 MHz is roughly 65 micrometer. In practical switching converter design, this effect is modeled by a parameter called AC resistance or ACR. Typically, ACR can be several times higher than DCR. And again, you can use either hand calculation or script or a SPICE model to account for this loss. By the way, this skin effect is caused by eddy current flowing in the wire. In interest of time, I'm also leaving out proximity effect out of this video. Proximity effect is also an AC loss and its effect is modeled into ACR. I want to spend some time in discussing what are our options in reducing these losses. These AC losses are function of switching frequency and peak-to-peak inductor current. For a given converter design, if you double the switching frequency, peak-to-peak inductor current halves. Now, both core losses and ACR losses are proportional to the frequency, but they are also proportional to the square of the current. So in this case, doubling the switching frequency actually reduces the core and ACR related losses, but it increases the switching losses. So overall, this may not be the most effective solution. If the converter is a fixed frequency converter, then operating in DCM can reduce the core losses significantly. In fact, if you have DCM option available, then reducing the switching frequency can also reduce the switching losses. and thus this becomes even more effective. In certain cases, choosing a higher value of inductor can be beneficial. This is because for a given design, a higher inductor value causes reduced inductor peak-to-peak current. But we want that a higher inductor in the same package comes with higher DCR and lower saturation current. So consider all other requirements before making this decision. By far the most efficient way to reduce core losses at low load current is to operate in PFM. At extremely low load current, you can reduce the switching frequency quite a lot, potentially without increasing peak-to-peak inductor current. So operating in PFM in general reduces all kind of losses. In the next video, we will consider losses due to parasitic diodes and BJT. So post your comments below and thanks for watching.